So, chapter 7 starts with the contributions of Isaac Einstein, and there's actually more contributions than he contributed. That's actually not in the book. Um, in fact, you notice they don't even say anything about the Einstein model of a solid in this chapter if you read it already, which is something that I've introduced, which was the thing that actually made him famous. It's the thing that made him well, not worldwide famous, but it's the thing that made him famous within the scientific community when he was a young man. It's the first big paper that he wrote when he was really, really young, and they don't even mention it in the chapter. But they do mention and there's also something else. The second thing he did actually is not also in the chapter, which also was pretty famous within scientific communities. It's something called the photoelectric effect that he discovered. Um, which has to do with quantum principles and the way that basically atoms take on energy, which was a huge breakthrough as well. And I think I'm not mistaken. I think he did get the Nobel Prize, but it's not for what you think. It wasn't for relativity and it wasn't for any of his like grand unification. I think it actually was for the model of a solid. I think. But it's kind of ironic that it's not for the things the more popular and well-known concepts that we know, and for the greatest being relativity. That equation E equals mc squared also comes out of that second thing that I just mentioned. It was something that he proposed uh, in the process of the photoelectric effect. Um, And the groundbreaking principle out of that was something called quantization of energy, which is what that formula embodies. Quantization, it means that when energy is absorbed by materials, it's kind of like, I guess it happens in packets. You could say that. Like, it's more like, I guess the way I would explain it is something like this. If you were like right now, I'm warming up some water because I have my spigot on, if you can hear it. So just think if you were filling up a bucket of water, you could take a hose and you could pour it in, and the water would go up gradually. At and the level that the bucket would be filled as it fills up is every level, every um, height of the bucket would be covered as the water fills up. Um, so that's one way you could fill up the bucket. But another way that you could fill up the bucket is take a measuring cup and fill up the measuring cup and pour water into the bucket at cups at a time. Now, in that case, there's only certain increments of, like, if you were to mark the level of the water after each filling, there are several heights within the bucket that not only would not be uh, the water would not actually go through. I mean, it would go through it, but not in kind of, well, in an ideal case, you could say that only the heights that are considered to be legitimate heights are those that are marked once you finish each cup of water, let's say. And so there are only certain heights that could actually be logged as uh, places where the water settled. And those places would be considered discrete points. and any other point would not be allowed for the water to be, as a legitimate mark where the water could be. That concept is called quantization. It means that as the bucket takes on water, there are only certain specific quantities of water that it can have because of the way that it takes on water. Whereas if you had a hose, because the water fills up gradually and continuously, all levels of the bucket could be filled. It turns out that on a relativistic level, and remember quantum level, and what we mean by that is on the level of atoms, um, and particles that are associated with atoms, like electrons and and protons and neutrons, things like that. On that level, all matter can only take in energy in a quantized fashion. It can only take in energy like pouring cups in, as opposed to using a hose to pour water in continuously. The whole universe is like that because the whole universe is made of quantum particles. Um, so it's deceiving that it's kind of like the difference between maybe a good analogy would be the hose would be like analog, and the cup of water pouring it in would be like digital or something. I don't know. It's not quite the same, but uh yeah. And you've probably heard of the photon, right? The photon is an individual corpuscle of energy. In fact, the photon is kind of like, in this analogy, the photon would be the cup. So when an atom or any material on a quantum level takes in energy, it takes in photons. Um, yeah. So that was a huge breakthrough uh, in our understanding of the universe because, energy is really, really important, as you probably know by now based on our discussion. So, um, actually, it's the photoelectric effect. I think that's what he got the Oscar for. I think not the Oscar, the Nobel Prize. So it was the second thing he did, and he still wasn't quite known. The second big thing he did in physics, and it's something that is not probably known by most people, but it's the thing that made him really, really famous within the scientific community. And yeah, I think he did this around between, I think, 1905 or something like that. And he didn't get the Oscar for it until about 10 years later, I think 1913 or 1915, something like that. The Oscar, I keep saying the Oscar, I meant the Nobel Prize. Well, they don't mention those two things, I don't believe, in your book here in the chapter, but that Mhm. I thought that they should be mentioned because, for obvious reasons. But they do start here with relativity. We can hit a few points there. Actually, they start with frames of reference. A frame of reference is really just a coordinate system. And I should probably say a word about that, quick word about frames of reference, because there's a particular kind of frame of reference that we actually take for granted here, that we use. Well, first Einstein and frame of reference. So, yeah, Albert Einstein, there's always standout physicists, right? And I guess Albert Einstein is the standout physicist from the 1900s. That would be the 20th century. I'll go ahead and mention those things that I said. So the model of a solid, photoelectric effect. Write down the famous equation E equals mc squared. We talked about that in this paper and proposed that. I think it was in that paper. And the principle of relativity, and there was two types. Well, I think they only talk about one type here. There is general relativity, which is quite complex, which they're the one they don't talk about here. And when they do talk about it, they actually doesn't look like they make a distinguish between the two. Einstein's theory of relativity hidden beneath this seemingly simple statement lies a view of the universe that is both strange and wonderful. The extraordinary theoretical effort required to understand consequences of this one simple assumption occupied Einstein during much of the first decades of the 20th century. Um, yeah, so it looks like they don't make a distinction. Oh, yeah, they do down the bottom. Special relativity and general relativity. Yeah, so actually, special relativity was published in 1905. So I guess these other things, because he had done them earlier, they were before that, these concepts I'm giving here. So we'll put that down. General relativity. Two types, general, special. Uh, Special deals with and tries to explain relativity in the context of inertial frames of reference, which I'll define briefly, and general relativity describes non-inertial reference frames of reference. And also one last thing that he discussed, and he didn't really create it, but he probably made the greatest inroads during that time with trying to understand and figure it out, is something called grand unification, which we haven't quite achieved even today. But he was the first person to really start working on it in a significant way, I think. Grand unification. I think I mentioned this before, which is the unification of all known, create all of the known forces, the fundamental forces, unification, which we've discussed: gravity, magnetic force, and the strong and weak nuclear forces. I think, to my understanding, we have combined the strong, weak, and the electromagnetic, but gravity is the big holdout. We still haven't been able to figure that out in a way that we can combine it with the other three. And yeah, so those are, I would say, Albert Einstein's major contributions in a nutshell. And I think he did a couple of some other things, but those that are kind of ancillary to that. That's a word. Anyway, yeah. So let's start with frames of reference. Frame of reference, as I said, is a coordinate system. And Einstein broke them up into two basic types of. One is an inertial frame of reference, and one is a non-inertial. Let's talk about inertial first. Examples of an inertial frame of reference are, and a frame of reference is like a coordinate system, like when you establish a coordinate system, on a problem. So let's say that we have a problem where we have a block that's sitting on a tabletop or on the ground. And generally what we do is come in and put in a coordinate system so we can measure its height, its length along the ground. And so what we would do is probably illustrate this problem something like this. So I usually do like a sketch and then a diagram. And specifically, I define a sketch as the stick figure of the picture of what's going on. So we'd have the ground there. This is a mass. And maybe I'll put a little flower there just to kind of give me a perspective of where I am, right? Whatever. So that's how I would start with any problem I create. It's actually as I said, a sketch of the problem. But then I start to quantify that by putting in vectors and quantities that represent the physical quantities, the quantities that I've identified, like the initial conditions. Like, if is it at rest or is its initial velocity non-zero or whatever. But the very first thing before I do all of that is you have to establish where you're measuring it from, because you could do a lot of things. I could measure it from the ground. I could measure it from the top of the object. I could measure it from a window, maybe above 20 meters or 20 feet above, whatever. You can do it wherever you want. So you have to establish that. So we generally do that by, as I said, putting in a coordinate system, which in general is called a frame of reference. So that's all it is, just a coordinate system. Now, there's something that we kind of take for granted about most coordinate systems, like the one I've drawn here. And that has to do with defining it as an inertial frame of reference. So let me put it in. So I'm going to generally do, I have my x-axis that's parallel to the ground. So superimposing in the axis, the mathematical axis onto my sketch does this. So that's what I mean by diagramming it. The diagram starts to put in the coordinate system and the mathematical vector quantities that represent physical quantities that I'm going to be using or identifying as initial conditions of that situation. Now, the thing that is inertial about this is that the reference frame is stuck. It's not moving. That's one thing. Well, and technically speaking, an inertial reference frame is one that is not accelerating. It actually can be moving, but it has to be moving at a constant velocity. And a constant velocity means, remember that velocity is a vector. So constant means that the reference frame can be moving, but only at a constant speed and only in a straight line. Because remember, if it changes direction, even if it's moving at a constant speed, that's still not constant velocity. It has an acceleration. We didn't talk about that so much because they haven't done that in this chapter. But like, if you have something that's moving around in a circle, for example, at a constant speed. Like say I take this thing and I move it around like this, like we assume that the speed is constant. Well, even though the speed is constant, the object is not its direction is consistently and constantly changing. So it has a certain type of acceleration that we call centripetal acceleration, just like the moon going around the earth. So that's not constant velocity. It's constant speed, but not constant velocity. So an inertial reference frame has no acceleration and moves in a straight and either does not move relative to other objects or moves with a constant speed in a straight line. Now, the reason that's important is the following. Let me just write that down. So inertial reference frame, so either no relative motion. Actually, over here. Or constant velocity. That means straight line and constant speed. And the reason this is important is because if it does accelerate, well, basically it means that there's not going to be any acceleration relative to other objects. If there were acceleration relative to other objects, then Newton's laws will break down. Newton's laws do not work in a non-inertial reference frame. At least they don't work in the way that we expect them to. And I can give you a very nice illustration of that. So let's say that um, you're riding in a car. You're riding in a car and you ride by someone on a stop that's on the that's on a that's standing at a stop sign. And let's say that you're moving at a constant velocity, so you're moving in a straight line. And let's say that your speed is let's say you're going slowly. So your speed is 5 miles per hour. Let's say that this blue box is the car and this marker is the person that's at the stop sign. Do it here. So the car is moving by at 5 miles per hour, constantly. Right? So when you look at the car, this is you. You're the marker you're the person at the stop sign. You see the car traveling by a certain direction at 5 miles per hour. So that's kind of like saying the coordinate system. We infer that there's a coordinate system stuck to the ground, like by us or by the stop sign, perhaps. We don't necessarily put a coordinate system out and do that, but when we're looking at objects around us, that's what we are implying, that we're measuring it relative to a frame of reference that's actually on the car. I mean, sorry, on the ground. We do that implicitly. But you could also think of the coordinate system being on the car. You could. So that the coordinate system of the person in the car is moving along with that person at 1 meter, at 5 meters per second in a straight line. So in that circumstance, when the person in the car looks at the person with the stop sign, the person in the stop sign is not standing still. Now we kind of make that assumption because even when we're in cars, we also assume that the coordinate system is on the ground. So if we see a person standing at a stop sign, because we know that a stop sign is stuck to the ground, and we everybody agrees collectively, we all agree that all of our coordinate systems are not moving on the ground, the person looks out of the car and says, oh, that person is not moving. But in fact, what Einstein came along and said is that that person is moving. He's moving relative to the person at the stop sign is moving relative to the person in the car. How fast is he moving? Well, it's relative. It's the same as the person's. He's moving. The person in the car is moving with the same speed relative to the person that's standing by the stop sign, as the person standing by the stop sign sees the person in the car moving relative to himself. So the speed is this would be the same. The person moving in the car sees the person standing at the stop sign moving in the opposite direction with the same speed. So that would be so let's take this room for example. It just so happens that to your left from the camera view, so to your left is north, and to your right, the direction that this car is moving is south. So the person standing at the stop sign would see the car moving 5 meters per second, 5 miles per hour south. But if I took a coordinate system and stuck it to the car, so like I have a X and Y axis on the car and they're moving along, then the person in the car sees the person at the stop sign moving north 5 meters, 5 miles per hour. But here's the thing that I want to say about the inertial reference frame. In both cases, even though you would calculate different relative speeds, I guess even relative velocities, both people would still see each object as having zero acceleration. So the person at the stop sign would look at the car and say, oh, that person is moving along at a constant velocity. They're not accelerating. And so, the acceleration would be zero. The person in the car also, remember, they wouldn't see technically he's not standing still. They would see him moving north at 5 meters per second, but his direction wouldn't be changing and the speed wouldn't be changing. So they both see the same acceleration. But even someone standing outside observing both of those. So say you've got a third person, me, for example, and I'm standing, down the road, or maybe whatever. We look at both of these. So I technically you could make that a different reference frame because I don't have to put it in the same position as the person that's at the stop sign because these still be on the ground but somewhere else. I see both of those individuals at a different position relative to my coordinate system, or different position that they think they are relative to their coordinate systems. But still, one is not moving and one is moving, but they still would have the zero acceleration, which is in line and is consistent with Newton's laws. So all of those examples, those individuals will have inertial reference frames because there's no acceleration that any reference frame would see relative to the other. And in that case, F equals ma, which is Newton's second law, and all of Newton's laws still work. Now, let's just change this question. So that's the example of an inertial reference frame. And what we can say is that Newton's laws of motion only work in well, let's say that at the end after I illustrate what a non-inertial reference frame is. So and then we'll move on. Non-inertial reference frame, and we'll just say accelerates. A non-inertial reference frame is an accelerating reference frame. Or accelerating coordinate system. And let me tell you why that's a problem. Let's go back to this simple example where the person is standing at a stop sign and watches a car. Now, because we see that all the time, all right? Say that there was a stop sign in addition to the stop sign, maybe stop sign east and west and stoplight north and south. So the car is at a stoplight, and the car, so the car is stopped and the person is not moving. So right now, two different reference frames, one on the ground, one on the car. Right now, they're both inertial. And the person looks out of the car and sees the person at the stop sign not moving. The person says, oh, that person has zero velocity. Person at the stop sign sees the car not moving. Oh, that car has zero velocity. Now look what happens. The light turns green, the car accelerates. The person at the stop sign says, oh, the car is accelerating with a certain acceleration, let's say 1 meter per second. Person in the car looks at the person at the stop sign, and what does that person see in the car? They see the person at the stop sign accelerating in the opposite direction with 1 meter per second. Someone tell me what's the problem with that? Why is that problematic? It's a little bit different than just the car moving at a constant velocity. What's different about it? And see if you can think in terms of Newton's second law. Why is it problematic that the person in the car sees the person at the stop sign now accelerating in the opposite direction at 1 meter per second? Why is that problem a problem? First of all, you do agree with me that technically the person in the car sees that, right? Because it's just relativity. I know we haven't defined relativity from Einstein, but you know, you can imagine that's from your personal experience. That's what you would see. Caitlin, do you first of all, do you agree that the person in the car sees the person moving in the opposite direction with the same acceleration magnitude? Yes, no. Okay. Can you take a stab at why that's a problem? What's problematic about that? Get my tea here. Mm. That- no. Okay, let me just tell you so we can move on. So remember that Newton's second law Well, does anyone remember what Newton's second law is? Been a few weeks since we mentioned it. Newton's second law says that in order for something to accelerate, it has to have a non-zero net force. So Newton's second law says that the net force on an object equals mass times acceleration. Newton's first says that the net force equals zero. That's one way to state it. Remember, the first law says that an object will stay at rest or in motion in a straight line unless acted upon by a net external force. So if there's no, so think of it this way. When you write the first and second law like this, the right side is the motion side, is the way I kind of teach it. And the left side is the force side. So if there's no net force, there's not going to be there will be no, now be careful, it's change in motion. Remember the first law, I made a big deal about the first law is written in the negative. So this doesn't represent motion, this represents change in motion, which is literally the definition of acceleration. Acceleration is the change in velocity, it's not velocity. So if you kind of think of Newton's laws, the first and second, as the right side is about motion and the left, that's, and this is when we write it conventionally like this, which most people do, right? So this is the motion side and this is the force side. So what this is telling you is that when there is basically, you're not going to get any change in motion when the net force is equal to zero. When the net force is non-zero, then you do get change in motion, right? You do get acceleration. So let's go back to this guy. What forces are on this guy when he's standing? Well, they're the same forces that are on this mass sitting on the ground, this block sitting on the table. There are two forces. We talked about that. One is basically I think, oof. Okay, so I gotta change that. One is is the weight, which is acting straight down. The weight, which is the mass times acceleration due to gravity. And the other force is the other force is essentially a contact force. It's the normal force. It's the force that's causing it to. Got my marker there, so I can ignite this thing here. Is the force of the table, or in this case, the ground on the object, and we call it a normal force. And it's equal and opposite to the weight. It's the thing that keeps the object from falling through the ground, essentially. And the reason that we know it has the same magnitude is because the object is not moving. If the normal force were greater than weight, then the object would actually move up. If the weight were greater than the normal force, then the force of gravity would pull the object through the earth, through the ground somehow. So they're equal and opposite. Normal force. It's not working. Yeah, so the forces are equal on this object. There's no, in other words, there's no non-zero net force, right? So why does it accelerate? How can it, oh, Julia. So that would mean that the car's speed is different from the person's because the person is definitely not moving. They both have the same mass. I would be wrong. No, it doesn't mean that. I think you're kind of overthinking it there. It doesn't, we're not talking about motion here, really. We're talking about the cause of the motion, the forces. The car has a certain mass, the guy has a certain mass. They're not the same. They have nothing, the masses don't have to be the same in any way whatsoever. They're not related. All I'm simply saying is that when this person starts to accelerate, he looks out of his car and spontaneously, that's a good word, this person just starts to basically accelerate in the opposite direction. But the thing that causes acceleration is a change in force, a non-zero net force. And there's nothing about the forces on that person that has changed, because this guy actually sees it. He sees that the person, if he could look at the forces on the object, they would just stay the same. It would just be weight down and normal force up. And all of a sudden, it would be unnatural, right? We don't think of it because we don't think in the way that Einstein did, but until he told us to. But this person just sitting there, all of a sudden they just shoot off. Why? You have to kind of look at it like an artist. You're standing in your car, you see the guy there. If you could light up the forces on him, be the weight down and the normal force. Now you move off, but all of it, but like if like if you could kind of black out the fact that you were in a car and that you were moving, like if you were in a black box or something like that, and you didn't realize you were in a car, all of a sudden, this guy would just start moving to the left. Why? Nothing changed about his forces. Now the guy sitting on the, standing at the stop sign, he sees the car move off, but that's not the same. Why is that? Because there's an engine. We know that there's an engine that's applying a force to the axle. That's what was different, because we know that the guy pressed the accelerator. So like the car, if the car is at the stop, this is what we see on the car. Car sitting there. When the car is not moving, he looks somewhat similar. It's a different mass, Julie, but still, the guy has its weight. So we'll call it the mass of the car and acceleration due to gravity. So we'll call it the weight of the car. So no, the car's weight is not the same as the man, but he does have a weight, and he does have a normal force that's going to be consistent with that. So the no, I'll call it N prime, because that normal force has to be equal and opposite of that weight. So when the car is just sitting there at the road, these are the forces that the man sees on the car. But when the car then starts to accelerate away from the stop sign or stoplight, if we could see the forces on the car when the accelerator is pressed, there's now a kind of an engine force that's now going to be in the direction of the acceleration. It pops up. We could see the vector pop up if we could see forces like that. So I call it F car. Well, there's no, and I guess technically we would also see at the same time a frictional force appear in the opposite direction of motion. But the frictional force is not going to be as big as the engine force. Otherwise, the car wouldn't move. So we'll call that friction. So in the horizontal direction, as soon as the guy presses the accelerator, this is what we see. Basically, Newton's second law. We see a net non-zero force in the x direction, and that's going to be equal to the mass of the car times the acceleration in the x direction. And if I were to build this out to put in the forces, I would write it out like this. Like on the right side, we would have a larger engine force, F car, minus a frictional force equals mass times acceleration. And therefore, if we took this difference here, we would get a non-zero result, assuming that the engine's force is greater than the frictional force, which in general it is when you're accelerating like that, or it has to be. And then you can back off the engine, once you get up to your speed. And in that case, the frictional force and the engine force, when you're moving down the road at a constant speed, you've kind of backed off the engine such that the frictional force and the engine force are the same. If you come off the accelerator, then the frictional force becomes greater than the engine force and the car slows down. For that, yeah. Would the person's speed be different from the car because the opposite direction they are facing? The velocity would be different, but first of all, the speed would not be constant. The speed would be increasing, and the person would be increasing at every point. The car would see that the person has the same speed that they do, but different velocity. So speed's increasing. The person would, again, it would seem that they have an acceleration.
So their velocity would be increasing to the right for some unknown reason. And at every point, whatever the magnitude of that speed would be, it would be the same magnitude of the car as the car accelerates along its direction. But again, the car has a reason to do that because along the horizontal direction, along its direction of motion, it has a non-zero force. But the person, it still looks like this. There are no forces in the horizontal direction, so there's no reason why that person should be accelerating. So again, all of this is what would happen if we took our coordinate system and pinned our coordinate system to the car and then used that coordinate system to measure all stuff. So that would be a non-inertial reference frame because you would be getting acceleration when you shouldn't, right? You would be getting acceleration just spontaneously when there's no obvious forces or non-zero net forces causing that acceleration. So that's the difference in an inertial reference frame and a non-inertial reference frame. Okay. Well, I hope that helps a little bit. Hope that helps a little bit. Yeah. Hope that helps a little bit. So now that we've basically described inertial and non-inertial reference frames, we can come back and actually make a point about Einstein's general and special relativity. Most people consider special relativity a little bit easier to understand because it's just uh, relativity within inertial reference frames where Newton's laws work. What general relativity is basically trying to extend the concept of relativity to non-inertial reference frames. Essentially, what Einstein tried to do is tried to correct his laws to work in basically tried to rewrite his it's essentially what it is doing. It's trying to rewrite his laws of motion so that they will work in non-inertial reference frames. And I don't know that he accomplished it. Actually, he didn't. He didn't quite accomplish it. As far as as far as I know, I don't think that he did because it's just crazily, it's just insanely difficult, as you can imagine. It's one thing to understand what a non-inertial reference frame is. It's another thing to try to come up with some laws such that you now get like basically what you would have to do is go back to that same scenario that I just described and try to come up with some laws to justify why this person just spontaneously accelerates. I have no idea how you do that. Because you can't really. The only way that you can do that is if you're in a third reference frame, and then you can describe both of the motions in that third reference frame, so that you can see that the accelerating reference frame is accelerating. The problem is that if you're in the reference frame, you don't know that you're accelerating. So how do you write laws to spontaneously to justify why some person just spontaneously starts to accelerate in some direction? Like I don't even know where to start. So that's you begin to see the problem with general relativity and why it's so difficult. And to my knowledge, I don't think that I know Einstein didn't do it by the time he died, so I don't think anybody else has done it since then. But I haven't. It's not really my area of physics, so I haven't. I don't really keep abreast of those things. But it's kind of changed. Honestly, it's not really. People don't call it grand unification anymore. They kind of changed their focus. But when you hear these cosmologists talking about the theory of everything and looking for dark matter and dark energy, the cosmologist, Einstein wasn't really a cosmologist, but that in fact cosmology didn't really exist at the time. He kind of he didn't create it, but he kind of pointed the direction, and him and a lot of other physicists during that time, the turn of the century between 1900 and 1925, we did manage to create quantum mechanics, by 1925, but that led to us being able to contemplate the stars and the universe in a larger fashion, and that basically led to the creation of cosmology. Um, and So the cosmologists now have kind of taken over, but they don't even call it grand unification anymore, but they call it the theory of everything. But if the cosmologists accomplish their goal, which is to understand essentially all the forces of the universe, it would encompass grand unification. So that's where that is going now. Yeah, so uh, we should at least state the basic principles of relativity before we leave. So let me just do that. They have them stated right here. Um, Albert Einstein thought long and hard about this paradox. So they kind of set up a paradox there. Yeah, I'll let you read through that. I won't read the book to you. I won't insult you. You can read the book by yourself. So I'm trying to give you things that aren't really said in the book about these concepts, so that can help fill in the gaps, maybe. But let's at least read the three uh, postulates associated with relativity. And a postulate, that's probably a word I should define. A postulate is just an assertion. It's just an assertion that's basically made by a person's observation of some sort of physical phenomena. So Einstein looks at the universe and he postulates these things and then builds up a theory from that. So a postulate, just in my own word, my own, you know, define it in my own words, is simply an assertion made um, about a so a specific assertion made about some physical phenomena, or made after upon observing. It's probably like that. Upon observing some phenomena. Well, phenomena is plural, and I've written set up the sentence to be singular, so phenomenon. So let's read them. The laws of nature are not the same in all frames of reference. An idea Einstein was not reluctant to accept on philosophical grounds. Now, an illustration of that is this example that I just gave. The laws of Newton's laws are not valid in a non-inertial reference frame for the reason that I illustrated. Prior to that, prior to people thinking about it, like they just didn't think about it. And it may seem something simple now, but you got to remember, people didn't even have cars back then, right? There were no cars. Uh, the Henry Ford didn't come along and do his thing until 1920s, or the early part. So it might be obvious to look on a road and like I just created this example, right, of accelerating car versus a non-accelerating car. People probably didn't even think about acceleration stuff because like you're on a horse and buggy. Sure, a horse and buggy must accelerate. Obviously, it does if you go from not moving to moving. But the acceleration is so small and over a so short a period of time, people don't even think of the concept of increasing velocity or even what a velocity is. You got to go back to that time period to see why this is so groundbreaking. Einstein starts to do this, like he's thinking about like speeds that we are accustomed to seeing all the time, and they weren't around him, right? This is how forward thinking he was. That's why he was brilliant, right? Like people, you're like, what are you talking about? Like, like the average person couldn't even picture it. So And like even any like we think about G forces, we know what they feel like because we made things like roller coasters. So we're on a roller coaster, we can we get the butterflies whenever you go real fast. People probably didn't even get butterflies. Where they gonna do it, right? Like they don't even know what that is, what that sensation is. So the sensation of moving down a hill real fast, they wouldn't do that, like unless they're about to crash and have a wreck or something and on a buggy that's out of control or they're falling off a cliff, or something like that. So the idea that that kind of motion, accelerated motion, feels very different than constant motion or decelerated motion where you slow down real fast and you feel your body compress. So they don't have any sensation of that or that there would be, some kind of difference. So for whatever reason, Einstein starts thinking about it. He's like, wait a minute, like if I were actually moving that fast or my acceleration was that high, would the laws be the same? Prior to that, I guess they assumed that they would be, but they're clearly not based on the example that I just gave. Maxwell's equations could be, so this gets into electromagnetic theory, but basically the same thing is happening with light, similar kinds of things. So Maxwell's equations could be wrong, and the speed of light depends on the speed of the source emitting the light, in spite of an abundant experiment in spite of abundant experimental support for the equations, uh, for support for the Jesus, I can't even read anymore. I can't see, that's why I need glasses. In spite of abundant experimental support for the equations. The equations being Maxwell's equations. So essentially, light moves, it's kind of the same thing that I did, the analogy that I just made for low speeds. If you don't have cars and things like that, it's hard to imagine you know, what happens when you're moving very fast. Well, relative to the speeds that we move, even speed of sound and things like that, light moves much, much faster. So, and like we know that when we're moving along, right? If I were to uh to move along in a car and then throw something out of the car, let's say not a car because we got friction involved in, and that would affect it quite a bit. But let's say that we're on a bicycle. And if I have a rock on a bicycle and I throw the rock while I'm riding on the bicycle, the speed of that rock is going to be the combination of the speed that it would have if I were throwing it by standing on the ground without moving and the speed of the bicycle. Now, I think our intuition is kind of leads us to know that that's true. I agree with you. Yeah, I'm gonna read the part of the chapter. Yeah, so we kind of know that to be true, right? So if I'm just like that's why we run like when you kind of want to throw something like you might take a couple steps and run forward. Like if I throw something and measure how far it is, like a football or something, on average it's going to be a certain different distance. But if I start run like with a javelin, like we just saw the Olympics this summer, people with a javelin they don't just stand there and throw the javelin. If they stand there and throw the javelin, then it's going to go a certain different distance on average. But if they run a few steps and then throw it, on average, it's always going to go farther. Why? Because it has a larger velocity leaving the hand. Why is that? Well, it's going to be the velocity of the acceleration of just the throw from the shoulder, the force from the shoulder. But if you add to that the speed that you're running, then the initial velocity of the javelin coming out of the person's hand is the combination of whatever natural speed it can give it by accelerating it with the throw, plus the constant speed or whatever the speed of their motion as they're running. So because it has a larger speed along with the running, it's simply just going to go farther. So we say that the velocities are additive, right? The velocity of the javelin is the combination of the speed from the throw and the speed of the motion of the athlete. It turns out that based on everything that we've measured in classical physics and you know basically now in terms of our science that we have now, light for some reason doesn't do that. It doesn't do that. If you take light and you put it on a spaceship, something that's moving very fast, like the space shuttle or whatever, or let's say that you have some spaceship moving out in space, like yeah, like the space shuttle. So I'm sitting on the space shuttle and I'm orbiting around the Earth. If I take the space shuttle and I open the bay and I'm sitting in space, I take a flashlight and I shine that flashlight and I go now when you're up in the space, I don't know what I can't rattle off the speed of the space shuttle, but it's going like very fast, like faster than the speed of light around the Earth. Much faster. I don't know how many times faster. Maybe I could ask Siri. Hey Siri, in terms of the speed of sound, how fast does the space shuttle move around the Earth? 25 times the speed of sound. So the speed of sound is about 300 meters per second. So like the sound barrier, like jets don't go. When you hear like Mach 3, Mach 5, that's 5 times the speed of sound. So that's how fast the fastest jet can go in the atmosphere. No more than 3 to 5 times the speed of sound. The space shuttle, when it's in any of these satellites, because you can see satellites at night. If you get that Elon Musk little app, it can tell you where satellites are. And on a clear night, you can look up and you can see them. You can see them moving across. So any of those satellites, they're going anywhere from 20 to probably 30 or 40 times the speed of sound, depending on how far out they are and stuff like that. So that gives you an intuition for that kind of speed. So that's fast, okay? That's fast. So you would think that if you're in a space shuttle or on a satellite and the satellite sends out some signal, that's a considerable amount of speed that should be added to the light, right? Based on the way things happen that are not moving at the speed of light, like us, here on the Earth. But and that's what they're saying there. All the ways that we tried to measure light, because we can actually do that, right? We do, right? We get signals coming back from they're not bent. We should, when we get signals coming back from the space shuttle or light or whatever, because, radio signals, that's just light, right? No matter what experiment that we've tested, the speed of light is still the speed of light. It doesn't change. Even if it's on the space shuttle going 25 times the speed of sound. We have not measured any incremental change in the speed of the light for whatever reason. Now, that's experimental. But what Einstein is saying is that he doesn't believe that. He doesn't know why that would be true. So his postulate is that Maxwell's equations should be wrong. Maxwell's equations are the equations that define the motion of light, basically. It's how James Clerk Maxwell was the guy who basically discovered the speed of light. So he put together a set of equations and he determined theoretically what the speed of light should be. 50 years later, when we measured the speed of light, we found out that he was right. So Maxwell's equations are kind of like Newton's laws, but for light in a way, in a sense. Let's just leave it at that. So basically, Einstein is saying that Maxwell's equations should be wrong. I don't know why they're not, but they should be wrong because that doesn't make any sense. And then the final postulate is our intuitions about the addition is basically what I just said. So our intuitions about the addition of velocity should be wrong, in which case the universe might be a very strange place indeed. So he doesn't know why that doesn't happen, with light in the universe, because we could say the same thing about stars, like the light coming from galaxies that we see, it's always the speed of light. And we know the galaxies are moving relative to us. So, now we can tell that they're shifting, the blue shift, the Doppler effect. I think I talked about that. Tell you about how the light Doppler shifts. So it shifts and everything, but we can take that into account. But for some reason, we always know that the source of the light coming from the galaxy, it seems to be going at the same speed. And that speed is 3 times 10 to the eighth meters per second. That's why we say that, light is constant. The speed of light is constant. It shouldn't be constant according to what the way we think it should behave, but it is, and we don't really know why. Why Einstein doesn't. Well, we don't actually. So those are those postulates. Those are the relative that those are that's special relativity. It's kind of well, that's not true. That's relativity in general. Those are the basic postulates. And then you can apply those to special relativity, and that's fine because special relativity is just basically, you the non-inertial reference frames, as I explained, and general relativity then tries to explain it for accelerating reference frames. So yeah, that's it. That's Einstein's deal. So let's move on. I spent a lot of time on that. We still got a couple things to talk about here. So basically, then they just say, okay, we're not going to talk about general relativity, but let's go into special relativity and then talk about some of the things that come out of that. And yeah, I'll let you. I'm not going to go through the experiment. I'll just say what they are. But basically, uh, this concept that I just made about like no matter how we see light coming from any source is always the same. That's a concept within special relativity. That's how light behaves, in inertial reference frames and from our point of view. So that's the first thing that comes that about special relativity is that we treat light like a constant, no matter where its source, no matter how fast its source is. Light is a constant, and that speed is 3 × 10⁸ meters per second. So, um, special relativity, light does not. The speed of light does not change. The symbol for light, the speed of light is c, and its magnitude is 3.0 times 10⁸ meters per second. Light is constant, or the speed of light is a constant. Now, let me tell you something else that happens, something called time dilation. We assume, and this may be because, well, whatever. I won't speculate on why it is. I'll just say what it is because we don't really know why. What is time dilation? It turns out, now this is an interesting concept, that when you start to go fast, well, what Einstein postulated is that when you're going at speeds close to the speed of light, you can observe that time is not the same. Essentially, the faster you go, the slower time goes. In fact, if you could actually achieve the speed of light, time would stop. Your clocks, your watches, they would all just stop. Time dilation, which is the case for you, the light clock. Yeah, light clock. Yeah. So you use light clock. So let me tell you. So there's this thought experiment that Einstein came up with, which is really kind of mind blowing. Let's say that you have a twin. It's actually probably much more than we think. And if you can use the tool quite significantly, or did my oh yes, for you, then it starts to that tool can get more sharper. What just happened? Well, hopefully you're still working over here. Like I can't see you or my looks like my phone is still working, but my other device is just cut off. Oh good. It glitched on my side. It's working now. Uh okay. I don't know what's happening to the signal. Why did the signal? Oh, oh my internet went out. But my phone has a hot spot, so that's why I didn't go out. Thank goodness. Okay. All right. So we got still got it rolling. The twin paradox. Let's say you have a twin, and one of your twins is an astronaut, and he can travel at the speed of light. So he goes out to Andromeda and he comes back. So I don't know how long it takes. I forget how far away Andromeda is. Certain number of light years. Yeah. Probably too long for. Let's say he doesn't go to Andromeda, but he goes out in space someplace. Maybe he goes to, I don't know, Saturn and comes back or something. And he's going at very fast, like at speed of light or close to it. Now he's got a watch, and his watch doesn't. It just stays the same. But as it turns out, the faster he goes, as he approaches the speed of light, his clock starts to, and basically, you synchronize before they left, the two twins synchronized their clocks. So the one twin gets in the spacecraft and goes off, comes back. While he's traveling, his clock, is working fine. It doesn't do it. It doesn't, it doesn't see any noticeable difference. But when he comes back, less time has transpired. In fact, years. His twin might be like 3 or 4 years older than he is. And each of their clocks were behaving normally relative to their perception. But the reason is because since the space traveler was regularly going at the speed of light, his time was dilating, was changing relative to the time of the clock on the Earth. So that's the general case. The faster you move, the more time slows down. Now, what people don't realize is that this idea of time dilation, there's no critical point where it starts. It's based just on relative motion. So, technically speaking, even when I walk across the room to get some tea, in my vicinity, time slows down relative to the walls or relative to everything else in the room. But it just happens with such a small error that it's not easily detectable. You'd have to be going like 2 or 3 or 4 times. Well, sorry, a half, 0.5. You have to be going like, a quarter or half or 3/4 the speed of light in order for you to be able to see some difference. You have to be going much faster than the speed of sound. No, it's not. Now I misspoke. I didn't mean 2 or 3 times. I meant like 1/3 or 1/2 or 1/4 or 3/4. But yeah, we do think it is faster, but that not in this case. This is a classical kind of thought experiment. So I misspoke. I meant to say 1/3 or 1/2, 3/4. But to answer your question is, yeah, there's something called quantum entanglement, where information is clearly passed almost instantaneously, which is fast, and no matter where you are in the universe. But that's a different topic for later on. So we used to think that no, you couldn't travel faster than the speed of light, but now there is literally experimental evidence, uh, namely the quantum entanglement, which can be set up and tested in the lab, that shows that information, i.e., light, can travel faster than the speed of light, and we don't know why. But yeah, but not in the situation I'm talking about now. This is not in this thought experiment. All right, so yeah, it's very interesting. So time dilation. So that's it. So they kind of create this experiment here to try to prove to you that that's true and why. And so I'll just let you read through that. It's really interesting. Really interesting. I'll let you do that. I'm not going to go through it. I'll let you just read through that. Probably have to read through it a couple times, but maybe to get it. But it just shows that essentially uh, the distance that this light beam travels when it's moving is going to be farther than the distance if it just goes straight up and down, right? Which is really clever way of showing that um, if you're on the light beam, then it takes longer to travel up and back and forth to the top and bottom of that thing than if you're standing still. So that's a great way of illustrating it in a kind of a without having to go because it doesn't really you don't have to go the speed of light to be able to see this example. Where in my case, it doesn't really illustrate it. You just have to believe me. But that's a great example. And so time dilation, and that's one thing that happens. And then they talk about the size of time dilation. Well, I guess it's just giving a relative. They divide, give some experience, and they derive that equation. So that's really good. I'll let you. I'm not going to go through and derive that. You can read through it, but the final result there that they give on page 157, they kind of bring this. It's a clever way of deriving. They basically just derive the. They can use classical means to derive basically the equations of motion that we've studied to derive an equation to show you how much the time dilates for this simple experiment. And they come up with that equation there. And so I'll leave it at that. Now, once you get that time, then you can use that for the other things that happen. So I'm going to move on. And what we show is that there's basically everything else associated with matter also dilates, meaning the size dilates, the mass changes. Now, I told you mass is an inherent quantity; it shouldn't change. But when you start to go faster than the speed of light, or not faster, but approach the speed of light, the mass changes. And also energy, the internal energy of the object, all of that changes. It's all different when you start to approach the speed of light. And so they just show this here. And one way that you get the difference is you just add on this, you just put on this quantity that they derive with time. Because we can describe all of those other quantities, uh, shape or length, we'll say, mass and energy, we can relate them to time. So once we know how much time dilates, then the amount that all those other quantities dilate, you just replace the time in the equations that relate those quantities with this factor that they come up with. And the factor actually has a name. I think they call it the Lorentz factor. You just throw in this Lorentz factor where there was time before, and that gives you the correction for the length contraction, the mass um, um, uh, the relative mass change and the relative energy change. And so all of that is what special relativity does. Einstein did that. He's the person that did this, that showed how that this must be true. Pretty brilliant, I think. So what I can just write here is that as we go into break, so time dilation, and I'll just write down the Lorentz factor, which is the correction. I'll put it up here. And that's regular time. I use the symbols that they use. Um, They use mg and what is that, cg? That stands for I think moving. What does the G stand for? Moving and very well. Yeah. Yeah. Um, and then divided by the Lorentz factor. I think it's E over C, right? Yeah. Square. That's right. So this Lorentz factor, these you have to read it, but the TM means that it's basically the moving clock. So it's you know how I said the twin, they synchronize their clocks and the twin and the spaceship moves off. Where we're assuming that the Earth is not really stationary, but we're assuming that the Earth is stationary as a ground. That's probably not a great. Well, I guess what it is, whatever. I guess it is. Um, the guy moves off from basically it means the first. These are two subscripts. The first subscript refers to the clock, and the second subscript refers to the observer on the ground. So M means moving, and so it means that the clock itself is moving relative to a stationary person on the ground. And uh, so, yeah, that's what this means. A moving clock and ground observer. That's what they have over there. And a ground observer means the observer is not moving. It's implied. And TGG means that basically it's like the guy has a watch on. So it means that it's a stationary clock and ground observer. So ground clock means it's not moving. And ground observer, sir. So ground implies no motion, the word ground. So TM would be like a clock that's moving close to the speed of light. And TGG would be a clock that's on the ground, basically someone's watch on their hand. So this equation gives how much the time of the clock that's moving has dilated, i.e., has slowed down relative to the clock, the watch on the person's hand. So basically, you can see that this is going to be a lower number than this because you're dividing it by something, right? TGG divided by 1 would just be the same value. So when you divide it by any non-zero number, then it's this guy is going to be less than this. So this shows you, because Einstein didn't know. As far as he know, time could speed up whenever you move, or it could stay the same. He didn't know. He just basically logically, so he concluded from this experiment that they show you here that it definitely must change, that the light must travel a larger distance in the same amount of time for the time that it would be if it was not moving. So that implies that um yeah, it's kind of hard to, yeah. So let me see if I can explain that. Um yeah, it's a little weird. So from our point of view, the time travels longer in the same amount of time. So it travels long, so it has to travel a farther distance, which means that it has to be traveling faster, which, well, it is, it's traveling the speed of light. But if you are on the object, it doesn't look like time has changed at all. Your clock is still moving at the same amount of time. So it must mean, if the perception of the person in the vehicle, the clock hasn't changed, it must mean that the concept of time has changed for that person. If the light has done the same thing, but from the point of view of the person on the ground, it has taken a longer distance to do that. So, from the point of view of the person on the ship, on the moving thing, their time is less. It means less, or it's basically it's slowed down. That's all I can say. And so this factor, going through that logic and deriving the equation, comes up with this factor that indeed it has decreased, and you get a dilation of time, and that it slows down. So yeah, I just have to let you read. You have to, you just have to kind of read through it a couple times so it sinks in some way. I did, like it did. I didn't get this even special relativity, which seems, it took me a while, right? I had to kind of think about it and read through this several times when I was first learning it. And even then, I think it probably took me it took me probably a month before, at least a year or so before I was able to teach it to someone. And I know I'm kind of just going really fast. I'm not actually going through the equations with you, but even it's, I still have to kind of prepare whenever I'm teaching it in order to really do it in a way that's really, you know, convincing, I think. But anyway, that's it. So once you have that factor developed, then all the others just kind of fall out. The others meaning distance, mass, and energy. So there is a length. It's called length contraction, although they didn't use that name here. So time dilation occurs, length contraction occurs. The interesting thing about length contraction is that it only happens in the direction of the motion that's close to the speed of light. So what you'll get is distorted figures. And they give an example here of the space shuttle. It doesn't actually, if you're moving along a horizontal, it only contracts in the direction of motion, but the width stays the same. So you get like this, kind of like those something that would look very similar to what would happen if you were at a circus or a fair, and you go into the clown room or something. It has all those mirrors, and you look in, you're doing all. That's kind of what would happen, but in the mirrors, it probably happens in all directions. But in terms of a special relativity, that contraction, that distortion would only happen along the direction of the velocity that's approaching the speed of light. So length contraction And I don't think they have a name that I know of for mass and energy that's kind of a catchy name. But see what they say here. Clocks run faster for stationary objects, distances. Mass is lowest for stationary objects. Moving masses become more massive. Yeah, I don't know. It's mass. Yeah, there's no word for it, but basically your mass increases. As I told you, if you're going the speed of light, if you actually are traveling and you're approaching the speed of light, uh, if you were to approach the speed of light, you would shrink down to a point, a singularity. You would have no size. You would have well only in the. Well, that's not true. Only along the length of the direction of travel. You would go to zero width or zero length along that direction. Your time would stop for you, so time would stop, and your mass would go to infinity. No matter what mass you are, at the point you reach the speed of light, those three things would happen. Time would stop. You would get zero length along the direction of travel, and your total mass would become infinite. Yeah. So mass increases. Let's say I would just call it that. Mass increases. And because mass increases, then energy would also increase to infinity as well. So energy increases. Your mass and your energy would become infinite at when you reach the speed of light. And we know this, right? Because you can get, this comes qualitatively out of Einstein's relationship that E equals mc squared. Well, if mass goes to infinity, then energy also has to go to infinity because the speed of light is a constant. So, and they should say that here somewhere or imply it. All objects contain a rest energy in addition to the kinetic energy potential. Oh, that's something else. So that's another. Oh, they say it there as well. Yeah, talk about it. Give out E equals mc squared. But that's another implication that I didn't mention that they mentioned there is that again, they're talking about close to the speed of light, but there's no critical point where that starts. So when I walk across the room, anytime you move, your mass increases. So like you're in your car going 50 miles an hour, you're actually more massive than when you're stationary. But the change is so small because the velocity is so much less than the speed of light, then it's practically negligible. I mean, we can't measure it, that is. But that actually is happening. Every time you move relative to something else, your length is contracting, your mass is increasing, your energy is increasing, and um, your time is slowing down anytime. So that's Einstein's special relativistic world. And yeah, oh, and then they go and they do mention something about general relativity. They kind of I think they try to talk about what it is. But my you can read what they say, but my example of the car and the non-inertial reference frame, that's the best way that I can explain it in kind of the first pass. But they kind of try to talk about something falling there, and then they talk about orbital motion. You can read through that, uh, but the upshot is basically what I said: is that you're going to get acceleration when there's no apparent reason for the acceleration, and that's a violation. So that's the basic first pass of understanding of general relativity and what it entails. Yeah, predictions of general relativity. But then they kind of get into a philosophical discussion of general relativity once you and some of the implications there. I'll let you read through that as well. Who can understand relativity? Great chapter to read. So I hope that helps you in some of your understanding. We'll take a break now. Before we break, any comments or questions? I really love your comments, Julia, and Caitlin as well. You've been commenting all along. But as we wrap it up, oh, when a rocket launches, it does break the sound barrier too. Yeah, that's true. Yeah, they break the sound barrier. Sound barrier is like in at 20 degrees Celsius, I think it's something like 330 meters per second. You know, uh, that's true. Would the person's speed be different from a car? Because I didn't see all these questions. You go back. Would the person's speed be different from the car because the opposite direction? Oh no, we did do that. Special relativity. It does talk about okay. Is it possibly faster than time? No, than time itself. Okay, well that's difficult because time doesn't really have a speed. So yeah. Time is really weird. I mean, we don't really understand what time is. When you start to get along these, basically what people are saying now is that time really literally doesn't exist. It's just somehow in we perceive time to be something that it's not. In other words, there is no time. That there is only one time, one moment, and that moment is now. In other words, one way I've heard it described is that anything that you can think of in the past and anything that you can think of in the future is all happening right now. Everything is simultaneously happening, even past events like things that happened thousands and hundreds of years ago or whatever. It's all happening right now. The stuff that we read in history books. Now, I don't understand that. I don't understand how it then can transpire. I really don't. And I don't think that most people do. But there are certain implications from the things that we do understand that are implying that what we perceive as time as passing is not actually happening. Now, the reason I know that we don't understand it, like we understand, so what I'm trying to say is that certain things that we do understand imply that this must be true. But in order to fully understand it, we would have to basically rewrite physics. And to my knowledge, nobody has done that yet. This has happened before. Now, these concepts that we talk about in terms of quantum mechanics and some of the things I talked about 200 years ago, they were just as difficult to fathom as what understanding time is right now. But these people like Einstein were able to make some progress. And so when we figured that out, we realized that we had to change physics, and we did change it. That's what quantum mechanics is. Quantum mechanics is basically the correction of Newton's laws. And you can kind of see it here. This represents this is not quantum mechanics, this is relativistic physics, but it was developed during the same time that quantum mechanics is. And it works out really nicely because look at this equation. This is only true whenever you're going speeds that are fast or close to the speed of light. Whenever this speed v is very small compared to the speed of light, this term is zero. So that this equation comes back to Tm equals Tmg equals Tgg, which means there's no time dilation. When you look at quantum mechanical equations and quantum mechanics, it's kind of like that. Well, to some degree, I guess. Well, relativist equations are not necessarily quantum mechanics. What I'll say is this: is that classical mechanics, F equals ma, the equations of motion. The reason that the error in those equations aren't obvious is because the objects are not very massive and are moving very slowly. When objects begin to move very fast, close to the speed of light and have large masses, or sorry, small masses, masses like the proton, my mass is 8 times 10 to the 1. The mass of a proton is 8 times 10 to the negative 20. Well, sorry, 6 point something, 6.67 times 10 to the negative 27. So those quantities don't behave when you use the equations of motion and Newton's laws to try to describe them. You don't get the right answers. So we had to rewrite quantum mechanics. So what's going to have to happen is, if we don't, as we begin to understand time better, there's going to be a new physics that's going to be called, like, I guess, to make the analogy, it would be like temporal mechanics, time mechanics, where we basically rewrite all of classical and quantum mechanics, but make these corrections in terms of our new understanding of time. Temporal, Temporal, I believe. Temporal mechanics is what we would have. Something, I don't know what they would call it, but that's probably what I would call it, because it would have to be a new mechanics based on our new understanding of time. Um, yeah. And once we understand that, it's probably going to be given another 50 to 100 years, maybe even less. It'll be something else. It probably is like infinite understanding as we unfold the layers of the universe and our understanding of the universe, which probably you could make an analogy of an onion, right? It's just layers and layers and layers. Um, anyway, any questions before we go to break? Well, I hope you find that discussion be interesting. We'll leave that chapter. We'll go into the next one. Well, much of the topics I've actually already discussed in this chapter, we can kind of maybe put it together in ways that they kind of consolidate it. So they talk about different models of the atom, basically three different ones: the Greek atom, the Rutherford atom, and what we ultimately kind of adopted as closer to being true, which is what I presented to you a few weeks ago, the Bohr atom. But he wasn't Niels Bohr, and I mentioned to you, he was actually featured in that movie, about the atom this summer, or whenever it was. When was it? Spring. It wasn't this summer, was it? Oppenheimer. So whenever Oppenheimer was, the movie starts off, he's in college in England, and then he ultimately kind of moves forward. He becomes a scientist, and early in his career, at some point, I think he goes to Germany and he talks to some scientists in a laboratory there. I think there are two or three of them. But that was, if you go to scroll to page 179, this guy Niels Bohr, that the guy who, yeah, I think that it was Bohr's lab. I think Niels Bohr was one of the people that well, they didn't say it really, they didn't focus on that in the film, but that was one of the people that he went to see. Um, to talk about basically quantum mechanics, because they were realizing that things weren't right and that they were having to kind of reformat Newton's equations and Newton's idea of matter in the universe. And so they were in the process of doing that. So Niels Bohr, 1885 to 1962. He was one of the orchestrators of quantum mechanics. So there were two people, three people basically, well, two people, but then one kind of reformatted it. So quantum mechanics were the new. So there was modern physics, the new physics, but that kind of led into quantum mechanics, which was the theoretical basis of modern physics, quantum. And people just refer to it as quantum mechanics now. They don't really. Well, yeah. So the orchestrators were Niels Bohr, Werner Heisenberg, a French physicist. So I don't know his first name, but his last name is Dirac. Those were the people who basically took all these experiments and things that happened from about 1895 to about 1910. And then they kind of reformatted in 1915, let's say, and then created quantum mechanics. And from that, we were able to do things like make an atom bomb and all this nuclear stuff, nuclear physics, all the reactors, is because we understood, the quantum, the atom, and understood what it was to a certain degree, good enough to make those devices and make that technology. But it was because these guys worked out the theory of what really was going on a quantum level. Now, as I said, we ultimately adopted the Bohr model of an atom, which is, I've already gone over that. That's the proton, neutron in the center, electrons around the outside. And it's not really, I talked about the fact that they don't really orbit around. It's more complicated than that. They don't really go into the depth of that complication here, but they do talk about the fact that they're energy levels, and that the closer you are to the atom, to the nucleus, the more locked in the electrons are, and it's harder to pull them away. In the same way that it's easier to pull Pluto away from its orbit as opposed to Venus or Mercury, because those planets are closer to the sun. So the energy that holds them into their orbit is much larger. Now, it's not quite as exact as is a direct analogy with atoms, because electrons all have the same mass, whereas the planets around the Earth, around the sun, don't. If they all had the same mass, then it would be harder. You could see that it definitely would be harder to pull the objects away from the sun that are closer. Jupiter is much more massive than any other planet. So, even though it's farther away than Mercury, Saturn, or Earth, it's going to be much harder to pull it away because the mass just overshadows everything. So it's not necessarily an analogous picture in that regard, but that's how atoms are. Like, because the masses of the electrons are the same, then the closer the electrons are to the nucleus, the harder it is to pull them away. No doubt about that. So the Bohr model of the atom is what we adopt as beginning to get us on the right track. But before that, there were a couple theories. There was a guy by the name of Rutherford, an Englishman. So he had a concept of the atom. And then the Greeks also took a stab at it. So I'll let you kind of read through that. um, I think the main distinction is that the Greeks didn't know anything about, they didn't really separate. They just said, the Greek, I think it was more like what Einstein said initially in his model, that they're just, you know, matter is made up of small corpuscles of smaller particles. They didn't distinguish between protons, neutrons, electrons, didn't say anything about anything like that. It said that they were made of smaller particles, which is true. And given that that's 4,000 years ago, that's a pretty good perception that maybe there are these smaller things that are the building blocks of matter. Rutherford comes along, and honestly, I forget what his the main difference in his model was. Let me see if I can pick it out real quick. The Rutherford model is that Ernest Rutherford. Oh, yes, what it is. So in the Rutherford model, it basically doesn't take into consideration quantum effects, meaning Rutherford thought that literally the electrons did orbit around the nucleus in the same way that planets orbit around the sun. And that's just not true because there's not enough energy that ultimately the electrons would fall into the nucleus. And so he didn't really know. And also, just based on gravity, he didn't give a reason why the protons don't just blow apart. Basically, he assumed that the nucleus was held together just by the gravitational attraction of the protons. But it doesn't account for, I mean, I don't even know if he gave an explanation for it but it doesn't account for the fact that the Coulomb force, the repulsive force, is greater than that. So there shouldn't be forces that the repulsive force of the protons, because they're like charge and they repel down in the nucleus, the gravity is not strong enough to hold them together. So he didn't really account for that. So just based on making the direct analogy that it's kind of like a planetary system is not enough, and his model with his atoms wouldn't be sustainable. And so that, along with other things, as I said, there's these other modern physics effects like the photoelectric effect and other things that we discovered. And again, it went from the period of about 1885 to about 1915, where technology increased and we could actually use technology to investigate what an atom does and put it under different circumstances, looked at how it behaved. And so we begin to see these effects on a quantum level that were not the same as on a macroscopic level. Hence, we created modern physics, which, as I said, led to quantum mechanics. The universe behaves differently. There are slightly different rules on a quantum level. Well, it's really the same rules, but those rules, they don't show themselves on our macroscopic level. So even though they're still operating, the effects are so small that we don't notice them. And so, yeah, there was no way that Newton had any way of knowing that because he didn't have the devices to be able to look at small objects that are moving very fast. And so that's why he didn't know. So anyway, it's basically like Rutherford model is a classical model, and it doesn't account for the quantum effects that we see, like being able to hold the atom together, the nucleus, and being able to keep the electrons from crashing into the nucleus. So that's the difference. And again, I kind of presented it. I gave you kind of a Rutherford picture, but I said that that's not really. I kind of talked about these quantum effects. Here in this chapter, they go through and talk about the quantum effects, like the electrons. They don't just orbit around; they're in different energy levels about the nucleus, and they can only. And it talks about the quantization. I talked about that earlier. That when you go from an electron to go from one level to another, it doesn't do that um, smoothly. It takes a certain critical amount of energy. And even though it's taking on energy, the electron will stay in that shell, even though it's becoming more energetic within the shell. But then at a certain critical level, it just jumps to the next level. So it's like a unit jump. It's like what we call a quantum jump, a quantization. And again, going back to the uh, the analogy I made of filling up a bucket of water. You have to do it with cups, and it can only fill up with cups. It can't be half a cup or two-thirds a cup. the bucket can only take on new water in 1 cup integrals. So that means that the levels of water in the bucket are only going to be at certain levels. That's kind of how an electron takes on energy, as opposed to continuously with the water from a hose, or energy going in continuously like that and causing an energy shift. So it discusses that a little bit, describes the part, the photon. The photon is the smallest amount of energy that can be existing in a light, in light, photon. And we are familiar with that term because of science fiction movies. Star Trek was probably the first one that, well, I don't know, a lot of the movies from the 50s, photon beams, photon accelerator, photon tractor beams, things like that. It's the smallest. Basically, the photon would be analogous to the cup. I think I said that earlier. That's the amount of energy. There's a certain amount of energy in a photon. All photons have that same amount of energy. And so when you look at more energy, it's basically just several photons put together. But you can't have any energy less than the energy in a photon that exists in light. Yeah. So then they talk about why quantum mechanics had to be created, the quantum jump, the quantum leap there they talk about. That quantum leap is what I just described in electrons jumping from one level to another. So yeah, you just go through and read it. They don't really, it's not much math that's going to be going on here, but go ahead and read through that, and kind of puts together a lot of things that I said. And what else do we have here? Well, it goes into electromagnetic spectrum and describes that. Um, let's talk about that just briefly a little bit. Again, we've talked about it before. Light is well. Now, when we use the term light, we're usually referring to visible light. But if you look there on page well, that's actually spectroscopy. That's not the electromagnetic waves. I should probably define spectroscopy and the emission spectra. Okay, let's talk about that a little bit. It's a really interesting thing that happens in nature. Uh, I'm probably going to diverge from, they're using gas and different types of gas to describe it. I'm going to come back and do something different, do it a little bit differently. But it does explain the idea why you can have a blue flame, a red flame, a yellow flame. But it's kind of maybe indirect. Something that's a bit more direct in terms of what's actually happening is something that you may have played with as a kid. Phosphorescent toys. I don't think I've discussed this, but if I did say it before, just bear with me. Just hear it again. I think I did this semester in this class. How many people had phosphorescent toys when you were a kid? Phosphorescent. I should probably write that word on the board. If I can spell it. And based on the element phosphorus, which does this naturally. But phosphorescent, it's basically material that glows in the dark. I think it's SCENT. Phosphorescent. Glows in the dark. So material that when you put it in light, it takes on energy, and then when you put it in, turn the light off, it continues to glow. Glow in the dark material. Back when I was a kid, you could buy these little glowing toys, or they would oftentimes the little kind of toys that you would get in cereal boxes or like Cracker Jack boxes. Sometimes they would be phosphorescent from what I remember from what chapter 8, the red, blue, and yellow flame is mercury being burnt, glow in the dark sticks. Yeah. Well, yeah, like the camping sticks, that's also phosphorus. When you break them and the two materials come together, that's two materials having reactions, but that's what phosphorus. But you can actually have solid material that you put close to light and then it takes on energy and it glows. So the sticks are a little bit different. The sticks, I think, are when you break them and there's these two chemicals that come together, and the reaction uh, causes phosphorescence to occur. Yeah, but all of it's kind of related, which is the element neon comes. Yeah, all of those in the periodic chart, neon and what are they? I guess there's the inert gases. uh, Neon, argon, krypton, uh, helium too to some degree, radon, xenon. Yeah, five of them. Those are well, they are called inert gases, but um, actually, to be honest with you, that's something a little bit different. They also can glow, but that's not quite the same process, I don't believe, for inert gases. So let me just tell you. So you know how I talked to you about the electrons, they can exist in certain energy levels. And in this book, they give the analogy of they're on page is it? But they're talking about Niels Bohr. They give a ground state. So they're talking about the excited state of electrons, and they kind of give the analogy of steps. Like, because like when you go up steps, you're going up to higher potential energy. So they're kind of making an analogy there with steps. So within one energy level, well, in energy levels can have sub levels where there's in an energy level, a general energy level, I think you can have different steps, but the energy levels themselves are also steps. So an electron can be in a ground state, meaning the natural level that it is. It would be kind of like in the, if you made the analogy with orbital motion, and again, it's not quite the same. It's not the same, but somehow if you could give a planet more energy temporarily, it would go to a higher orbit, a orbit farther away from the sun, because with more energy, it can't stay in the same orbit. It's kind of like satellites, right? You can have satellites also at different levels orbiting around the Earth, but if they're orbiting at different levels, they have to, even if they're the same mass, they would have to have different energies because they have to be moving faster. The closer you get to the Earth, you have to move faster, so it definitely would have more kinetic energy. It just basically that's what an energy level is. It's like the farther you are away from some central object that has its own kind of energy, you have to have a certain amount of energy to be at that level. And if you switch levels, the energy has to change. Generally speaking, uh, so if an electron is existing at a certain step, in order to make it move to a higher step, you have to put in, it has to absorb energy from some external force. So like you could shine light on it and the light has photons in the wave. It's kind of like a microwave. That's in a sense, that's not an atom, right? It's the water molecule that's absorbing the energy, but it's kind of what I told you. I've talked about that before, where I told you that the water molecule has to have a similar frequency to that of the microwave. And because it does, it absorbs it, it starts to vibrate more and it gets more energy. And so then it goes to a higher state. It vibrates higher, with a larger energy, and it heats up. You can give it so much energy that it actually changes its phase and goes to a gas, basically evaporates and leaves the liquid. So to some degree, it's kind of like that. The electrons, they have energy in their certain states, but there's a certain frequency associated with their motion within that state, their vibration at that state. It's a certain frequency. If you shine an external light on it, it could be white light, it could be a microwave, any kind of wave, radio wave, anything. Even like friction, we can give it conductive heat. That could do it. But under certain circumstances, it takes on energy. It absorbs that energy if that energy has a frequency or several frequencies that are close to the frequency of vibration of the electron at that state. If it does, it can absorb the energy. But when it absorbs the energy, it can absorb a certain amount, a certain critical amount, where it can't exist in that state, that energy level anymore. So it has to jump to a higher energy level. It's like going to a different step, one step or two steps above where its ground state, its normal state is. Now, here's the thing. So that's what happens when you take phosphorescent material like a toy and you put it close to the light. It's the electrons in the atoms are absorbing photons from the visible light that is hitting that material on an atomic level. When those electrons get excited and they jump to a different state, it turns off, and this is just a fundamental aspect of the way our universe works. Whenever electrons do that, they give off their own energy for some reason. And they give off energy that basically they give off a photon that has a frequency that's related to the gap of the energy that they're jumping. And so it's radiation. It's radiation that's coming off whenever they jump up to a higher energy level. But it turns out that for phosphorescent material, that radiation that it gives off, our eyes are sensitive to it. So we see the light there because that's how it manifests. The photon being given off in the jump manifests as an electromagnetic wave, a light being coming from that particular source, that source of that electron. So all the electrons doing that together, collectively, it looks like light coming from the source, and that's what the glow is. And it's all the same frequency because frequency is associated with color. So when you see the phosphorescent purple or the phosphorescent green, whatever, that color is associated with the frequency of light that is being given off by the electron that is emitted when the by the photon that is emitted when the electron jumps to a higher energy level. And so all the electrons jump to those high, and it does that for a long time. But then the electron, it'll stay up in that state for a certain amount of time, but then it's losing energy gradually. And again, when it gets below a critical point of energy loss, it jumps back down to the lower ground state again. And every time it does that jump, it whether it jumps up or jumps back, it gives off a photon, and we see that photon as a glow. Um, so that's how that material works. That's what phosphorescence is. So there are a bunch of questions that were coming in. Let me look at them. Hydrogen peroxide is inside of the glow stick, which is a hard solid part. Yeah, or maybe peroxide and something else, though. I think they're usually a combination. So basically, what's going on there is you've got a chemical reaction going on, and in that chemical reaction, it generates heat, and the heat causes the electrons in those chemicals to do what I just said. So there's a couple ways you can cause the electrons to jump around. One is by external exposing it to an external heat source. Another is getting heat from a chemical reaction, which is what happens when you break the stick and the two chemicals come together to give a chemical reaction. And then the atoms in those chemicals can get heat and it starts to jump, and that's why it glows. Um, so I had some phosphorescent glow in the dark ball that came from the game of jacks. Yeah. Yeah. Um, would the colors that are neon be more likely to be phosphorescent than normal colors like neon yellow versus orange, original yellow? I'm not sure I understand that question. Um, oh, do you have one? Oh my gosh. Was that Julia? Hey, Julia. Oh, wow. Awesome. Cool. That's a glow stick, huh? Yeah. So cool. Do you use those for camping? What is it? What do you use those for? Like emergency or something? Thank you, Julia, for demonstrating that. Yeah, emergencies. Yeah. Awesome. Cool. Caitlin was asking about the colors. Would the colors that are neon be more likely to be phosphorescent than normal colors, like neon yellow versus original? Yeah. You know, I'm actually drawing a blank on the inert gases. I'm not sure why they glow. I think it's, oh, I think I'm remembering now. So the inert glass gases, we use them in like lights, right? Like neon is the cheapest one, but all of them you can. But some of them I think are dangerous. Like if you go up to the library, you can see I'm in Hollywood here, and you can look up at the observatory up there from my window here. They have a Tesla coil, and in that Tesla coil, I think they have this neon. I don't know still know if they run it now. They had shut it down a couple years ago. But in there, they had like a neon light that spelled out Tesla's name or something like that in different colors. Yeah, it's charged by electrical current. Yeah, so what happens, I think actually the same process now that I'm remembering. So in the case of the phosphor, what I'm calling phosphorescence, it's taking on light from a visible light. But again, the electron has to get on energy. In the case of the glow stick, it's coming from the chemical reaction. In the case of neon lights, it's coming from the electrical current. So what happens is you have these gas particles within a tube, and then you electrify it. And the electricity gives the atoms of that gas energy, but the energy is taken on by the electrons. And when they get enough energy, they jump levels. So it is the same kind of process, but just different ways of absorbing that energy. And it's electrical energy that's causing the electrons, that the electrons absorb and then jump to the different energy levels. And the reasons that the colors are different is because the atoms, the electrons have different energies required to cause them to jump. I think they call it a threat. Einstein, I think it's related to the photoelectric effect. Again, photoelectric. That's why he called it that. It's called a threshold energy. I was saying it's a critical energy because not all of the atoms, it's not the same energy that will cause them to jump. It's different energies. But because they're different energies, for all the inert gases, whenever that electron jumps, it happens to give off a photon that's within the range that we can see. And the different colors correspond to the different frequency associated with that energy of that emitted radiation, that emitted photon. Um, and so that's what it is. I'm pretty sure that's the kind of the general explanation for that. I have one actually near me. Yeah, that's so cool. Yeah, very cool. So I don't know, blue, was it, what do you know what materials, was it hydrogen peroxide? I don't know. Julia, was that what was in your glow stick? I guess so. Is that what it said? It's probably a mixture of some things. I don't know what causing that reaction. Yeah. Yeah, cool, cool, cool. Well, basically all of these on the atomic level, the same thing is happening. That's what causes something to glow. An electron can take on energy from some source, whether it be an external visible light, whether it be a chemical reaction, whether it be electrical energy in the case of a neon light bulb, and some threshold energy beyond that, it allows the electrons and all the atoms to jump to different energy levels. When they do that, they give off a photon in a photon in the context of radiation, which has a frequency and wavelength that's sensitive to, of which our eyes are sensitive. And it's interesting. I think the question you're asking is kind of the tone, the nature of the color. Is that what you're asking? Like why it looks that way? What we call kind of a phosphor, like a glowing tone. Because even when you don't see it in the middle of the night, like if you just see it in the daytime, like that, it has a certain tonal quality that's different than some other kind of blue. Um, that's a great question. I'm not sure. I mean, it certainly has something to do with. I think the reason. This is what I think. This is what I think. We don't really look at most light beams. We don't look directly at them. But it's the same reason that a neon light has a different quality than a regular conventional light. And it just, I guess my answer would be is that that is just the way the nature of. So when we're looking at light from like the eye of a stove or a regular like a conventional light beam, that thing is heated up because the filament itself has gotten so hot that it's glowing. But I think that's kind of like it's like fire, right? It's like and I'm drawing a blank as to why it's glowing, what causes it to glow. It gets so hot, but it's the same way. Like I think that whatever is causing that thing to heat up in that way, it's not necessarily. I don't think it's the same thing as, and I don't know what the process is, so I apologize about why it's glowing. It has to do with black body radiation. I think it's certainly the emission of photons, but it's not the same. And I can't quite remember the difference as to what is happening when the electrons are jumping energy levels. So what you're seeing is the difference between an electromagnetic wave and the reflection of light because of something heating up. And so it just looks that tonal difference is the difference in which our eyes perceive those two types of light, basically. But with the phosphorescent, with the you're literally seeing an electromagnetic wave that is traveling to you, and that is the color of that electromagnetic wave. Um, and so it has that kind of tone. It's like it's light. It is light itself. Yeah, I don't know. I'm not. That's not a very good explanation, and why that's different than like the eye of your stove. Um, yeah. Another reason is because when stuff glows like that, it's a combination of all different frequencies. So white light has a different. It looks different than a light coming from a neon light because it's all the same frequency and wavelength, and so that also can contribute to the tonal quality. Yeah. Yes, hydrogen peroxide, but it is a hard solution unless when you snap it and releases that chemical. It's glass tube on the inside. Yeah, so it's what I'm saying. That glass tube, I don't know. I don't know what the other chemical is, but I think what it is there's hydrogen pro. Okay, but that glass tube has some other kind of chemical, so that when you break it, they mix, and that mix causes the chemical reaction. That's or either there's the other chemicals on the outside and the hydrogen peroxide is on the inside. Um, and I'm guessing it's the hydrogen that's the active ingredient with the other chemical. I think that's what's happening. there's some sort of chemical reaction. That chemical reaction causes heat. Then that heat can be absorbed by either the atoms, the electrons in one of the atoms of those chemicals, and then you start this process of the jumping of the electrons back and forth in different energy levels. I'm pretty sure that's what's going on. So you have an exothermic reaction, which can start the process of the absorption of heat by the electrons. Yeah, cool. Well, I think that's pretty much that chapter that gets that done. Um, they just talk about how we use these this phenomena in different devices, and then they wrap up the chapter with the electron shells. So the shells are the thing I've been talking about this whole time. The electron shells. Those are what I was calling energy levels. They call them shells, SHELLS. So the different shells have the different energy, and the electrons can jump back and forth. And so yeah, that's what that is. And more complex atoms, like bigger atoms, have more shells because they have more electrons to house. But the shells are the way in which the electrons are organized about the nucleus of the atom. Cool, cool beans. Well, that's chapter 8. Hmm. Chapter 9, again, a lot of stuff I've already presented with quantum mechanics. I'll go ahead and get into it because kind of set it up because there's a lot of things here that they talk about the quantum entanglement over there at the end of the chapter. It's kind of a short chapter, but they do discuss, basically they set up the thing that I've already discussed to you, why we needed quantum mechanics. And that's the first paragraph they start off with, the world of the very small. They start off by saying that things behave different on the quantum level than they do on the macroscopic level. And so we had to come up with new physics to be able to describe it. And yeah. Let me just set up some things there. I'll talk about measurement. I'm going to take a little break here, about 5 minutes, and then we'll come back. You take a little bit of break, and then we'll come back, and I'll most of some I've only one or two things I haven't kind of hit on in this chapter already, so might be able to kind of pretty much finish this chapter because we got 30 minutes, right? Kind of put things together for you, but I've given a lot of all the background really already, so I can jump right in. There looks like there's about three concepts that they focus on in quantum, some of which I haven't discussed. But you remember how I told you, like with relativity, there were those postulates. Remember, I defined what a postulate is? There's one big assumption, big postulate that quantum mechanics showed us that is completely not obvious in the macroscopic world. And I'll spend some time talking about that because that's kind of the setup that you need to understand because that gives kind of the big picture of why the quantum world behaves so differently from the macroscopic world. And again, everything that behaves that is true in the quantum world is actually true in the macroscopic world. It's just that the effects are so small that you don't see them unless you have very sensitive instruments. And when classical mechanics was created, when Newton was around, he didn't. Now, I have a feeling that Newton actually suspected, but he didn't have the instruments to measure. And so one of the cardinal rules in science is if you can't measure it, it's not, you can't say anything about it. Not that it's not true. You can speculate, but why? Because if you can't prove it, then it's just a speculation. And it didn't really help us anyway because we didn't really need it. All Newton's laws works fine for us because our world just wasn't sensitive enough to be able to tell the difference. So anyway, let's take five. I'll come back. So it's five, right? Let's come back at 10 after, and then we'll continue.